Hi, this is Jonathan Gardner, and we're covering section 1.7 of Schroeder's An Introduction to Thermal Physics. And this is the section on rates of processes. And it starts off with a couple of paragraphs. First, he talks about how typically when we discuss thermodynamics, we only consider what happens after things come into equilibrium. There is another field of study that's quite separate that is called transport theory, or kinetics. Now, honestly, I haven't studied transport theory or kinetics. The amount that I have studied in college is about what's covered in this book. So some very basic concepts he's going to go over in this section about how heat is moved, how the transport happens. And we're going to cover not just heat, but also diffusion and some other things as well. So this first part of this section, and it's a very long section, is called heat conduction. So when we have a hot object and a cold object, so we have something with a high temperature and we have something with a low temperature and there is heat flowing between it, we call that Q, okay? In this case, this guy is losing Q and this guy is gaining Q. There are several ways that heat can flow, right? One way is if there is only empty space, then we only consider radiation, okay? There is also convection. What convection is when a mass of liquid or fluid or gas moves to carry the heat away. And then we also have conduction. Okay, so the way you can think about this is if you have a fire, so you have a campfire, and there's my beautiful drawing of a campfire, there's some wood in there, okay? So the heat that comes out this way, this is due to radiation. The heat that comes out this way, this is due to convection. And if you were to grab the hot coals, that would be convection. So that would be conduction on the inside there. Okay? So, and you can basically see the strength of these processes. So radiation is fairly weak, right? So if you're standing near a fire, you feel the heat of it. But if you were to stand over the fire at the same distance, you would quickly be burnt to a crisp, right? And conduction as well. I think that we're more concerned about conduction because of the specific, the localized effect of that heat transfer, whereas convection is moving a large quantity of air. If you were to touch a hot coal, it would be only touching a small part of your skin, and so that heat would transfer and hurt you. But as we'll see in this section, conduction really isn't that big of a deal. In fact, it's not very significant at all compared to convection, okay? So how does conduction work? Well, when you have a barrier between two substances, right? So we have temperature 1 on this side, temperature 2 on this side, and you have the atoms and molecules or whatever moving around, then sometimes these atoms or molecules will cross or they'll hit the barrier, and then these guys will cross that direction. So there's energy being transferred both ways through collisions. But because the average kinetic energy on this side is greater, then it will transfer that average kinetic energy to this side, causing an increase in the temperature. Okay. Now note that conduction is related to electrical conduction. There's a relation between electrically conductive substances and the amount of conduction that happens. That's why you'll find copper is a great conductor of heat energy, whereas things that don't conduct electricity very well, insulators, are not very good conductors of electrical energy. Okay, and the reason for that is because the particles that are moving around in a conductor, in an electrical conductor, are electrons, and electrons are quite good at transferring their energy and moving throughout the entire system and moving that energy deep into the system, right? Let's try to derive the mathematical formula for how conduction occurs, how quickly it occurs, and what it looks like in the material that's conducting the heat. So for our example, we are going to consider a substance, like let's say a pane of glass, and we're going to have temperature 2 on this side, temperature 1 on that side. And in this case, we're going to say that it's cold outside, it's winter. Certainly turning cold now as the season changes from summer to autumn for us in the northern hemisphere here. And so we're going to see the heat energy flow throughout the substance, right? So there's going to be Q. So over here we have minus Q, and over here we have plus Q. Okay, and we're going to take a cross section, an area A of this material. Okay, so if we were to guess what that formula might look like, we might say if we increase the thickness, then that would be inversely proportional to the amount of energy. Like if we took two windows and glued them together, only half as much energy would be transferred through the window. We might guess that if we increase the area proportionally, more energy would flow as well. And we might guess that the change in temperature would also increase the energy flow. Noting that if the two temperatures were the same, there would be no heat energy transfer at all. So these factors, so we have the change in the position X, we have the area, and we have the change in the temperature between the two sides of the glass. And we would think that the energy that flows through there is somehow proportional to these, such that the energy that flows through, the heat energy, is proportional to the area, it's proportional to the change in temperature, and it's proportional to the amount of time that we take. Time is another consideration we have to consider. And the thicker it is, the less it is. So this is just a rough guess. Okay, so we can rewrite this as saying Q over delta T as in time. So the rate of heat flow is proportional to the area times the change in the temperature over the distance traveled, right? And so we can rewrite that as some kind of differential equation. If temperature is solely a function of the position, so we're fixing these guys, the temperature is not changing over time, then we would see that the temperature on this side of the glass would be the same as T2, on this side of the glass would be the same as T1, and there's going to be a temperature differential as you travel along the glass in the X direction. Okay? And we're going to rewrite this as an equation called the Fourier heat conduction law. We're going to say Q is equal to minus K sub T times the area times the thickness, the heat gradient of the substance, right? So the temperature over the position. This was discovered by Fourier, who proposed it. This K is called KT, but in Fourier's rule, in Fourier's heat conduction law, it's just simply K. So we're going to call it KT to distinguish it from Boltzmann's constant. Remember, Boltzmann was kind of the capstone on thermodynamics. So he brought in that constant as the kinetic theory of how thermodynamics works. And it wasn't, after he passed away, a couple years after that, his work was finally recognized and physicists finally accepted the atomic nature of matter. So this KT is renamed that to allow us to use K for the Boltzmann constant. Okay. Now, what is KT? There are a couple ways that we could find KT, and one way that we could find it is we could calculate using some complicated understanding of how the molecular model of heat conduction works. We could think about like vibrations traveling through a substance or something like that. However, rather than do that, we're just going to treat KT as a property of particular substances. I'll write in the top right hand here the formula. So Q equals minus KT times the area times the temperature gradient over the distance. Okay. The KTs that you'll find will vary quite a bit. Okay. So the units of KT is going to be watts per meter Kelvin. So meter degree Kelvin. Okay. So air has a KT of 0.2026. Okay, that's watts per meter Kelvin. Okay, water has a KT of 0.6. Wood is 0.08. Iron is 80. And copper is 400. So the general rule of thumb is if it conducts electricity well, it's a good heat conductor. And you can see copper is much better than iron. Water is a better conductor than wood, which is better than air. And so there's a relationship there. Now you might be surprised that air rates so low, because you know that if you put something into air, that it will quickly lose heat. The reason why air is so low is because the actual conduction, so the energy transferred at the boundary between the air and the substance, is very low. What does happen, however, is there is a very rapid convection effect that's happening. So as that air warms up, it quickly escapes and brings in new cold air to quickly sap the heat away. So let's do a calculation. So our window has an area of 1 square meter. So is equal to 1 meter squared. It has a thickness. So thickness is 3.2 millimeters, or 1/8 of an inch. It's a thin sheet of glass. If the temperature inside, so T2 is 20 degrees Celsius, the temperature outside, T1 is 0 degrees Celsius, then delta T is 20. So we can calculate Q over delta time. So the heat flow is equal to, well, we had, where's glass? Glass is 0.8. I missed glass. So we have 0.8 watts per meter Kelvin. Then we have 1 meter squared for the area. Okay. And then we have, 20 degrees Kelvin difference. Okay. And then the distance it travels is 32 millimeters, which is 0.0032 meters. Okay. And so if you do all that math, you'll get 5,000 watts. That's the amount of energy that's being transferred due to the difference in temperature. So he notes that this is a very high number. And the reason why he says that this is not really accurate is because this is basically if you took a hot plate and a cold plate on both sides of the glass. However, air itself, when you have the boundary with the glass in between, you have to consider that there is air on both sides. So it's not that the immediate surface here is 20 degrees Celsius. Over here it's 20 C, and over here it's 0 degrees C, and there's going to be a temperature gradient as well that uses the air itself, and air is a much better insulator than glass is. And if you actually measure in real life the Q over delta T of this, you're going to get a number somewhere in the neighborhood of a few hundred watts. Okay, in real life. There are problems here. They're fairly mechanical. Not a lot of theory here. Problem 157, a lot of units you need to pay attention to calculate the R value. 158 gives you the R value of a wall, and 159 wants you to calculate the heat loss through a house in a cold climate. Okay. And he wants you to calculate how much it costs to keep that house warm using electrical or natural gas. And so you measure natural gas and electrical energy in different units. So it's a lot of unit conversions, okay? And he actually gives you some values for how much it costs in his areas for electricity and natural gas. 160 has to do with calculating how long it takes for the handle to be too hot to grab on a frying pan, right? So let me just kind of illustrate this one. So you have a frying pan, and there's obviously a burner, there's heat here, okay? And so the frying pan is heated instantly to 200 degrees Celsius, okay? And this is obviously room temperature, so this is 20 degrees Celsius, something like that. And you want to know how long it takes for the heat to transfer from here to make it too hot to grab. So probably a temperature that's too hot to grab. I'm not very good at Celsius, but I'd probably say about 150 Fahrenheit would be too hot to grab. So you can do the translation for yourself. You can use a different unit if you want, a different number if you want to. Okay. And he gives you some units for the specific heat of iron and the density. And 161, so this is talking about how much energy the Earth is losing based on drilling holes. Okay. That's fairly interesting. 162 is a more involved problem. This is probably more challenging because it involves calculus and things like that. So in this one, you're going to derive the heat equation. The heat equation follows this form where it comes out to be like this. So the temperature at position X at time T is equal to the initial temperature plus the area divided by the square root of the time spent, E to the minus X squared divided by 4 capital KT. And this K is not the Boltzmann constant. This K is the KT that we just discussed divided by the C, the heat capacity per mass, the specific heat, and rho, the mass density. Okay, and so the equation that you start with is this dt by dt, temperature by time, is equal to this capital K d squared t by dx squared. So if you haven't done differential equations, you wouldn't even know what to do with this one. Besides, this one's a partial differential equation. How would you derive that from the heat flowing? First of all, deriving this is going to be a challenge for you. Second of all, getting the solution here. What you can do is just plug the solution in and see what happens. So if you're not familiar with partial differential equations, then you might have some trouble with this. If you want help with this, you can reach out to me. Your professor just might tell you to skip this problem and come back to it later when you know more about math. Anyway, guys, I hope you enjoyed this. We're going to continue with conductivity of an ideal gas in the next section. And the next section after that is viscosity. And then diffusion. And that should be the end of chapter 1. Have a great day. Take care. And bye-bye.